we'll see introduction to composite materials in engineering. Agenda for today's talk is introduction, basics of materials. I will little see what are the materials and what are different properties. Then definition of composite material, because this seminar is webinar is focused on composite materials, and difference between alloys and composites, because we normally know metallic materials, alloys, and then came composites. Then types and applications of composite materials, then significance of composite materials, and we'll also see current trends in the market and what are all the job opportunities in the area of composites technology and engineering. Then future, like why to learn more on composites. Materials matters, okay, as you all know. Whatever be the material, may be it metallic, non-metallic, composites, or anything, like natural materials like wood, anything you take, no, so that what for any construction, considering starting from human body to an engineering marvel like a pilotless target aircraft or an commercial aircraft, so everything is made up of one or the other different materials. So that's where the material matters. So materials, take a pointer. Yeah. So materials that are used in construction of man-made structures and components are called as engineering materials. Okay. So that's the, there may be materials available, or we make we manufacture materials and then use for different applications. Those are called as engineering materials. Selection of material system for any application involves multiple and challenging requirements. So you may be aware, like if you want to select a material for an automobile application, you need to have a set of properties defined in that material. Okay, so that's how the different materials got evolved, and still research and development going on in that area of materials. And materials must exhibit a set of demanding properties. They need to be producible in multiple product forms and have consistent high quality. So this is again coming back to the end application or a specific application. So all the materials we use needs to satisfy demanding properties, and also they have to be producible in different form shapes. Okay, like sometimes we may need in a sheet form, sometimes we may need in a forging, sometimes we may need a casting, sometimes we may need a composite laminate or a composite structure as such. Okay, so that is another requirement. Then materials research and development is influenced by engineering imperatives. Okay, both if it is metallic or non-metallic or composite materials. So the end application, the drive for the final application always drives the material R&D, research and development. To give an example, if you consider nowadays we want all electric aircraft or the renewable energy. Okay, so we are extinguishing the fossil fuels, so we need more and more energy, and more renewable energies, and less energy losses while we consume the energy or transport the energy. Okay, so that cases again we need to invent new materials, or we have to enhance the properties of existing materials. Okay, so that's all that comes into the materials research and development part. Okay, so this all in crux says like how materials are important in our day-to-day life today, and what is further important significance materials drive going forward. Now, so basics of the materials. So like as I mentioned, engineering materials, which is man-made materials but tailored to the end application. So how these engineering materials revolves, or what are the importance properties or importance of these materials, we'll see in this slide. So first we start with structure. Okay, so the material structure is the basic building block for any property or end application we derive from that material. Okay, so there are different types of bonds we have: atomic bond, crystalline bond or crystalline structure, then amorphous structure, semi-crystalline structure, and polymer chain. So like atomic bond is anyway, any material is consists of atomic bond. Then in atomic bond we have different types: covalent bond, ionic bond, metallic bond, all those things. Okay, then crystalline, it may be polymer or metals, and then amorphous materials. Then semi-crystalline, it is again for family of polymers like PEEK or polypropylene, they have little semi-crystalline structure, and then polymer chains like rubbers or polymers which have that chain, polymer chains, and then cross-linking happens, and then we get that end properties. Now coming to properties, we have broadly we categorize into two: physical and chemical and mechanical. So coming to physical, the melting point of that material, specific heat, thermal conductivity, thermal expansion, electrical conductivity, magnetic properties, corrosion or corrosion resistance. So the sum of importance of some of these properties, no, thermal conductivity. Sometimes we want materials to have very high thermal conductivity so that the heat dissipation happens quick. But sometimes we don't want that heat dissipation to happen quickly, so we don't want high thermal conductivity. And then thermal expansion, so especially thermal expansion coefficients. Sometimes especially like in gas turbine engines, we have those blades at very micron level tip clearance. So if this material at high temperature and running speed, if the material grows, then the tip clearance comes down. Okay, so and or the seizing may happen. So that cases we don't want the high thermal expansion, but some cases we need high thermal expansion. Okay, electrical conductivity, magnetic properties. So like magnetic properties are nowadays more important because, as I mentioned, no, the renewable energy or electrical energy getting into more and more importance. So magnetic materials or magnetic properties are important. Then corrosion resistance is key. Okay, any material, why it gets corroded is it goes to its natural state. Natural state of any material is oxide. Okay, like if you take any ore, it is iron oxide, magnesium oxide, silicon oxide, like this. So all natural available materials are in oxide state because oxide state is the most stable state. So whenever you have any metal or alloy, it tries to go back to the natural state and it gets corroded. But we need to prevent that corrosion, or we need to delay that corrosion so that we use that material for more time duration, so that durability increases. And then another important properties are mechanical properties like strength, ductility, elasticity, stiffness, hardness, toughness, fatigue, creep, resistance to wear, again corrosion, oxidation, high temperature properties. So these all things, no, I think you are aware, like each and every property here, it is very important. Okay, when it comes to a application, or when it comes to a durability, quality, reliability, so these all properties will say very important. Okay, so normally like strength, ductility goes hand in hand. So we sometimes we need very strength material, but same time it should have little ductility, otherwise it will break, it will have more, it become more brittle. So that's why. So then elasticity, stiffness, so we need good stiffness when we have a long slender structure, so that buckling strength comes from the high stiffness. Okay, so that's where, like sometimes if you compare steel versus titanium, steel has a very high stiffness. Okay, titanium doesn't have that good stiffness. Okay, that's why the different material comes into picture, different properties we evaluate. Again, fatigue, creep, especially when it comes to rotating components. Okay, fatigue and creep plays a very important role. Then resistance to corrosion or resistance to wear. Okay, when we have a control surface parts or a gear transmission items components where we need very high wear resistance, surface hardness required, so then we have different methods to build into that. Okay, so then high temperature properties, again in aerospace application or high-end automobile application or industry like heating industries or heat treatment furnaces, there and all we need a high temperature capability materials. Okay, so this like to give an insight that how these different properties play a very important role when it comes to engineering materials. Then heat treatment is mainly for metallic materials. Due by heat treating or by giving an additional thermal treatment to that material, how we improve those properties. Okay, like annealing, tempering, normalizing, hardening. Okay, so like sometimes we have hardening for a complete material, or sometimes only for surface hardening. Okay, so that is when I come to surface modification, I'll explain on that. And combining materials, so we said, or we the people invented the different types of metallic materials, different type of non-metallic materials. Then people thought, okay, that set of metallic materials have some advantages, some set of non-metallic materials have advantages, or different metallic materials itself can be combined. And that came the alloying and reinforcement within alloying or within the metallic materials, or then came composites. Okay, so composites, we'll give we'll see the details of composite little later. So these are like primarily three different types of materials where we combine different materials together. Again, come to engineering materials deriving the end application. Okay. Then surface modification. So we have different alloys, metals, composites, everything. But some cases we need a surface protection or surface improvement, surface properties improvements. That time what we'll go for a plating coating again to minimize the corrosion or increase the corrosion resistance. All those things will have plating coating. So plating coating can be done to any material, be it metallic, non-metallic, all kinds of material. But nitriding is mainly done, nitriding and carburizing done to metallic materials, especially steels. So advantage here is we'll have a soft core of that component, but very hard surface. Okay, so that's where we will fulfill all the requirements of high strength, ductility, everything. Same time, we'll get this good wear resistance. Okay, by just modifying the surfaces. So this is in crux the engineering materials, their different property, structure, and then how we can improve their properties, and then how we can combine different materials and come up with more relevant, more advanced engineering materials, and then finally to the surface modification to further improvise or improve the application perspective. Then coming to application requirements. Okay, I was telling in the previous slide, so what engineering material itself is derived from the end application, but what are those application requirements when we come to the different industries? Okay, so coming to mechanical industries, what we need is high temperature materials for gas turbines, jet engines, etc., and that is for increased efficiency and wear resistance mainly. But this is not the only the limit like requirement. There are hundreds of other requirements. Coming to electrical engineering, so electrical devices or machines can be operated at a faster rate with minimum power consumption. Okay, this is where the materials we look for, like the materials with properties. Those materials should have the very good electrical capability or electrical conductivity, and the equipment or devices should operate with less power consumption. Okay, and one is power consumption. Second is today's the challenge is power loss. Okay, when you transmit the power or when you make the power to go and like electrical power to perform that function, the power loss is more than power consumption some cases. So how we come up with different materials where we make those electrical energy is very much efficient. Okay, so that's where we are further developing on materials, and there came, like I was mentioning about the transmission loss, so there came the superconducting materials. Okay, so when why superconducting material is when the material is made to superconduct, the loss is almost zero. Okay, so that whatever energy you generate, it is all available for use. Okay, so that's the great thing. Okay, so this again derives or devices into the material application or the material invention. Then coming to aerospace and automobile, materials having high strength to weight ratio, so we need like less weight material. Okay, to carry more load, that gives a fuel efficiency. Okay, more reliability and more producibility. Okay, and again, as I mentioned, these are not the exhaustive list of property requirements, but these are the main property requirements when it comes to applications. Further continuing on that, electronic engineering. Okay, electrical we saw, but in electronics, material that are useful in the fabrication and miniaturization of electronic devices. Okay, miniaturization, you can imagine. So when I think 40-50 years back, when the first computer invented, the one small the computer with the smallest capacity or capability used to occupy a big room. Okay, can you imagine the computer is in like one single computer occupying a whole room size. Okay, today we have a iPhone or a mobile which can do all the functions, but imagine the size. It is just half your palm size. Okay, from a computer of whole room size to a device of palm size. How it happened? It happened because the material invention, that different materials got invented, semiconductors or the high computing devices. Okay, and again the miniaturization. Okay, so again, no, you can imagine, you need to have that floppy disk. Okay, when 30 years back, we all used that floppy disk, and again that each floppy disk can store a few MBs of data. Okay, but we have today smallest pen drives, and they can hold data of terabytes. Okay, so this also because of material invention, materials development, that miniaturization can become possible. And last but not the least, again, chemical engineering. So okay, in chemical engineering we need highly corrosion resistant material, because you handle those chemical substances or the high temperature chemical reactions happening. So there the material should withstand the high corrosion resistance. Like to give an example, the nuclear reactors. So nuclear reactor is the what you say, that the stringent norms, or the highest worst case scenario, the reactions happening, no, but the materials made it possible. Okay, you can contain that reactions and still generate that electricity, okay, because of nuclear reactions or nuclear industry. Okay, so these all things like gives you an insight how materials got evolved, and from application point of view what are the requirements and how further we are continuing on that. Okay, so then that's where I covered this all, the introduction or the overview of materials as such. Now I was mentioning that the properties or end requirements drives the material research and development. Okay, and realizing those materials, exotic materials, has given so much advantages to industries, like as I mentioned, a computer or storage devices or a mobile phone. Okay, so like that, and aerospace. Okay, so like when the Wright brothers first took their plane in 1903, it lasted for only 12 seconds. Okay, and today we have a flight for about 18 hours non-stop. Okay, how this can happen? So there are many technological inventions gone there, but materials also played an important role. Okay, then as I was mentioning, the material, they said, like one side we have a metallic materials, one side we have non-metallic materials. How can we combine two, or within non-metallic materials, how can we combine different materials and come up with a new material? There came the composite material. Okay, a composite material is a combination of two or more materials with different physical and chemical properties. So this is a point to be noted. Okay, so two different materials you are combining, but entirely both have different two or more different materials, but all have different characteristics, different properties. But in a metallic material alloy, it is not like that. So you are trying to combine two or three metallic elements with one or two non-metallic elements. Okay, but those metallic elements have similar properties, like they can conduct electricity, they can conduct thermal thermal heat. Okay, so like that, but they may have luster. But in composite, all constituents have entirely different properties. Okay, but when combined, they create a material which has better properties than individual constituents and is specialized to do a certain job. For instance, to become stronger, lighter, or resistant to electricity. Okay, so stronger, lighter, especially comes to aerospace application, and sometimes we use it in electrical applications where we don't want conductivity, so there it is becomes electrical resistance. So given further insight to that, like see, I said two or more different constituents. So say fiber is a reinforcing element, matrix is a matrix, soft matrix. Combine that, you get a composite. In composite, there are different varieties. We'll see little later. Again, this picture indicates the different fiber or different reinforcement, how the composite become. Like this is a fiber composite. The fibers are reinforced. Then particulate composite, particle composite. So what is small particles are introduced into the matrix. Then laminar composite. This is like these type of fiber composite laid one above the other and made a laminar. Okay, lamina. Okay, lamina of composites. Then flake composites. So reinforcement is like flakes. Okay, maybe graphite flakes or carbon flakes, like that. Then filled composites. Okay, this will have more reinforcement amount, but it is like a filled. Okay, depending on different application. So these different varieties of reinforcement we could give into composites and make composites. Further on to that, do you know our bone is a composite material? Have you thought ever? Yes, it is a composite material. Okay, and it is best known natural composite material, again along with wood. Wood is also natural composite material. Okay, what it is? Wood is made up of a cellulose fibers. The fibers are reinforcement, the load carrying members in a lignin matrix, and bone is a hydroxyapatite particles in a colline matrix. Okay, see that these both wood and bone uh, classifies as a composite material. A composite material is typically made up of relatively strong stiff fibers in a tough resin matrix. Okay, so why this tough resin matrix is no? So again, no, as I said, each and every individual constituent of composites has its own role and responsibility. Okay, so reinforcement will be stiff, strong fibers, so that they act as a main load carrying member in the composite, whereas resin is a tough matrix which holds the fibers together and which acts as a load transferring medium, and also it protects the fibers from the environmental damage. Okay, these are the main um, functions of reinforcement and the matrix in composite. Then coming going little more into the composite. So man-made composite materials used in aerospace and other industries are mainly carbon fiber reinforced plastic. So you normally come across CFRPs and glass fiber reinforced plastic, GFRPs, which consists of carbon and glass fiber respectively. Okay, in the polymer matrix, if you add carbon fiber as a reinforcement, it becomes CFRP, and if you add a glass fiber, it becomes GFRP. Both these fibers are stiff and strong brittle, but in a polymer matrix which is tough. So together these two constituents gives that advantage or optimized properties for these FRP composites. By combining these fibers and resin with complementary properties in this way, a composite material with most or all of the benefits. Okay, I said the reinforcement has its own advantages, benefits, and matrix has its own advantages, benefits. So when you combine two, it will give better properties, and it will also retain its own individual consistent properties like high strength, stiffness, toughness, and low density is obtained. Okay, so that is another advantage why we went for composites. Okay, by combining different materials and making them optimized for the properties, we are reducing the weight of that component. Okay, weight reduction is the biggest requirement in comes to aerospace, or in to some extent in automobile, or into any industry, consider even for a construction. The first carbon fiber was patented in 1961. See, it is not that old technology. It is very new technology. It's about 40 years, 50 years back, and then become commercially available. And see, 1990 is about 30, 31 years back, composites were starting to become increasingly common for manufacturing process and construction. Okay, construction means not civil construction, is construction in any vehicles like automobile, aerospace, space stations or space launch systems. Okay, so all those things. Okay, so that's all gives you insight on how the composite started and how we are today. Okay, today aircrafts with more than 50% composites flying. Okay, and again coming to space launch systems, or a next generation transport system like flying cars. Okay, they all will have more and more composite materials because of all this advantage like less weight, high strength, high stiffness, high toughness, high corrosion resistance, high environmental resistance, all these things. Okay, but only main limitation in composites when it comes to carbon fiber or glass fiber reinforced, the electrical conductivity. So for that we will have a different mechanism to embed there to have that lightning strike protection when it comes to aerospace application, and aerospace application for a structural outside the interface which sees the environment. Okay. Difference between alloys and composites, I briefly explained on that. Alloy is defined as a mixture of minimum of two elements in which one must be metal. Okay, so that is like if you say steel, it is made up of carbon, iron, and then any other additional metallic materials like molybdenum, tungsten, chromium, all those things. So it is like it scores more onto metallic side. Okay, so because only carbon may be the non-metallic there. But when it comes to composite is defined as a mixture of two or more elements for which the metal is not required at all. Okay, all can be non-metallic, or even it can be metallic, because I will explain little detail on that, because when we come to MMCs, metal matrix composites, we will have metal as a matrix. Okay, matrix material is metal, but other than that, all other composites are all normally non-metallic.